Direttamente dalla Sala.
Okay, so welcome and welcome to Paola. It is really a pleasure to have her here presenting her activity. Paola got a degree in Padova and then moved to Munich to get a PhD with Hans Böhringer and the group there at Max Planck. And since 2021 is ISO staff, or now has a role in the Office for Science as a deputy of the office. And in particular in 2021 and 2022, she got a ERC consolidator grant to investigate indeed the baryon distribution from galaxy groups to galaxy cluster. That will be indeed the topic of our presentation. So welcome, Paola, and go ahead.
Thank you. Thank you very much for the invitation. It's such a pleasure to be here also because there are so many friends in the audience. What I would like to present today is a clever view on the halo baryonification, which is nothing else than the process, a name for a process that is responsible for redistributing baryons in halos across time. It's a clever view, not because we think we are particularly smarter than others, but it's just like an acronym of the project of the consolidator grant. And I would like to highlight in particular the great work of the young researcher, the early career scientists that are working with me at ISO, and of which I hope I will give enough credit and show the results during this talk. So I would like to start from this picture. This is what we know about galaxy groups, in particular from an X-ray point of view. Those are two summarizing results of what we know about X-ray properties of galaxy groups. You see here the X-ray luminosity halo mass relation, M500, the mass contained within a radius where the mass density is 500 times the critical density of the universe. And then there you have the fraction of gas, of hot gas contained in halos as a function of the halo mass as well. And as you see, groups in principle, like small galaxies, should be the majorities, should account for the majority of the realized halos in our universe according to the halo mass function. But as you see, we have few groups. Why you would expect many more there, only few are observable, have been observed actually in the X-ray until the recent past. And indeed, when I started the project, this is the situation I faced. In principle, back in 2022, we had just 30-50 groups X-ray selected, observed in the X-rays in the local universe, while other 40-60 groups were selected in the optical and observed in the X-ray in the very local universe in below redshift 0.05, but over an area as larger as the eROS, the all-sky survey by the rosat satellite. And as you see, the same area, let's just focus on the SDSS, for example, 10,000 square degrees, should host at least 1,000 of such tiny groups in the very same volume. So all our knowledge about the X-ray properties of groups, which are very important, I will explain you why, were based on the 5% of the population, those actually visible in the X-rays. And why this could have been a bias, and I hope I will convince you that it was a bias. Well, hydrodynamical simulation, our models about the distribution of baryons in groups suggest us that the way AGN feedback, so the feedback by the supermassive black hole, also in the central massive galaxies at the center of these real halos, might have a strong impact on how baryons, and in particular, the hot gas is distributed within halos. So here we have the example of 4 different simulations for a group about 2 times 10 to the 13 solar masses compared to a cluster of 2 10 to 15 solar masses in halo mass. And as you can see, different simulations implement different feedback, leading to strikingly different results. From super X-ray bright groups, we are very dense concentration in the center and a uniform temperature distribution, to a very strong feedback from the central galaxy that push away completely the gas and lead to groups completely gas depleted. And as you can see in this picture, the situation is very different from cluster, where most of the effects are mostly in terms of entropy in the core of the structure. For groups, the effect is in the all virial area, so leading to gas depleted and X-ray faint groups. What does it mean? It means that if you want to know how much gas, how many baryons, how much baryons there is in such group, if it's redistributed, and you look just in the X-ray, you might be biased because large part of this structure might be gas depleted and so very X-ray faint if the AGN feedback has done its job properly and strong in at the direction. And so we started to look into this. As I show you, back to 2022, just a few groups were available. So we wanted to check what eROSITA was seeing. eROSITA is a relatively new satellite, German satellites observing the sky to give an all-sky survey. The results are based, at least what I will show here, on the deepest survey of eROSITA in EFETS, which is a relatively tiny region compared to the all-sky survey, 120 square degree, but it is and it will be the deepest available survey done by the satellites. Everything else will be much shallower. So we went to look at how many galaxy groups as a function of the halo mass we could detect in the X-rays. And in this particular plot, we pissed off a lot, all the X-ray people in the community working in this field. The red histogram is indicating how many halos or extended emission have been identified as a function of the real mass by the satellites, so visible and detected in the X-rays, while the orange histogram is the prediction of Millennium XXL, purely embodied simulation done with SAM populated with galaxies. And as you can see, the difference is striking. So already at 10 to 13.5, eROSITA was able to see in the deepest survey a tiny, tiny fraction of the virial regions predicted for that area. The blue histogram instead is giving the view of the optically selected groups, those not selected in the X-ray according to the X-ray emission of the hot gas and the quantity of hot gas, but based on the clustering properties of the galaxy members of the group. And in this particular plot, I plot only groups that have a multiplicity higher than 4, so more than 5 galaxies, and apply the same kind of selection to the Millennium XXL data. But as you can see, there is much more agreement between what we see in the optical, but a large difference compared to what we see in the X-ray. Why? Because if we expect that the AGN feedback has done its job during the lifetime of the halos, most of the groups must be depleted of gas. They must not be visible in the X-ray. And so the X-ray selection per se would lead to a street light effect. We look for the baryons, not where they are, but where we can see. Instead, if you want to have a clear view of the matter is distributed across halos of different masses, we need to look also where there is no X-ray light, where they do not shine. And to do that, we try to have a different approach. So we are going to study the X-ray properties of group, the average X-ray properties, but rather than select them in the X-ray, We select them through a different mean in the optical, where they are not, the selection is not affected by the same properties we want to study. We stack all of them, use them as a prior in beams of halo mass, and then we use the stacked image to infer the properties, the mean properties of the gas per halo mass. And so we use the EFETS area, where we have the deepest eROSITA area. But stacking is a tricky business. When you stack data, you stack many different kind of halos because you don't know what you are going to stack, if not the priors. In our case, was the halo mass. And so to check for any kind of bias or problems in the stacking technique itself, we use forward modeling. So we use the magneticum pathfinder simulation to create through FOX, which is a dedicated tool for creating X-ray events from another dynamical simulation, and 60, another tool to transform those X-ray events through the lens of the instrument we're going to use, in this particular case, eROSITA. And we use this tool to create mock eROSITA observation of many square degrees, based on magneticum. Why magneticum? Because magneticum was calibrated to reproduce the measure is X-ray scaling relation for clusters, and was the one best matching what we would expect for groups. So that was the main reason behind it. And of course, since we are using optical data for selecting our groups, in parallel to the mock eROSITA observation from the very same light cone, we produced also mock galaxy sample to use them to fed the available algorithm for group identification from the optical point of view, and test not only the stacking technique, but testing also our priors and all the information of the priors. So we create exactly the same simulated mock data sets as we use for the real observation to test all aspects of the data processing end to end. Okay, so in this way, we could clearly see, at least according to magneticum, that we check contamination and completeness and test that the optical algorithm for selected groups can lead to a much higher completeness and a very low contamination compared to the X-ray selection itself. The solid line here, the black solid line, is the completeness of the X-ray selection based on the same tool used by eROSITA for the real data. And as you can see, the completeness dropped down already at 10 to 13.5 solar masses per group. So eROSITA is able to detect up to redshift 4.2 only the massive cluster and a very tiny fraction of the group population, while the X-ray, the optical selection, has a much higher completeness. And the same is true also for the contamination, very low for the optical and a bit higher in terms of groups for the X-ray selection. The analysis in magneticum showed also that this kind of discrepancy is due to the fact that high entropy cores, high entropy groups, which are those that should be mostly affected by the AGN feedback, are X-ray faint and cannot be picked by the satellite, cannot be observed by the satellite, and the X-ray selection instead is limited to the low entropy and X-ray bright groups. We use the same forward model to understand which kind of contamination in terms of X-ray emission we might have. Here is the X-ray supervisory profile of groups in different halo mass bins in the mock observation up to redshift 4.2. So I will always focus only in the local universe. And you can see color-coded here the different contribution to the X-ray emission of groups from AGN, the X-ray binaries, the intragroup medium, which is what we are after, and then in blue, the total emission, the sum of all this contribution. And as you can see also from the model itself, we see that in particular, the AGN contribution is dominating the X-ray emission, the surface brightness profile at very low halo masses, about Milky Way type groups, 10 to 12.5 solar masses, while the intragroup medium the green line, the green area here, is dominated for the most massive group. Of course, this is a contamination that we need to take into account, because what we are after is isolating the intergroup medium. We want to know how much is the gas in the hot phase to constrain theoretical model, and we need to identify that contribution among all the others. So we use that information actually to inform our stacking. In addition to that, another source of uncertainty in the stacking technique is the accuracy of the priors used for the stacking. Not only the coordinates of your group, but also how you bind them in terms of halo mass. And so we tested the accuracy of our halo mass proxy based on the total optical luminosity of the groups through different kind of optical detection algorithm for group. You can see here the one of Robotan et al. 2011 in red, Temple et al. That is going to be used also for Euclid and other surgical waves as well, 2017, and the Young et al. 2005 catalog algorithm, which is the most large and most extensively used in the SDSS, and also is going to be used for DAISY. Stacking in halo mass proxy means that we are making we have an uncertainty due to the accuracy of the halo mass proxy itself, because when you bin and you stack, if you are contaminated by many groups that are in different halo mass bin actual, at a different actual halo mass, you might either dilute your signal or push it through bright sources. So we took that into account to inform our error mass budget in order to include in any measurement also this kind of information. And we tested the results of the stacking technique, comparing input and output in magneticum. The points are the stacked surface brightness profile for different algorithms, while the shaded region, the green region I show in the previous plot, is the contribution only of the intergroup medium already corrected for what we do here is we obtain the surface pattern profile already corrected for the AGN contamination, the X-ray the X-ray binary contamination, so to isolate only the hot gas. And as you can see, we do a reasonable work. The job is well done in the sense that the input is consistent with the output, apart from a particular case in one halo mass bin. And so we do the same also from the spectral point of view, in the sense we have also a spectral stacking technique to retrieve the average spectrum of X-ray groups, of galaxy groups as a function of the halo mass bin, to retrieve the temperature, and ultimately, but we are not there yet, to retrieve also the entropy profile of the group. And as you can see in this plot here, this is still the comparison between the input from magneticum and the output of the stacking technique. The input is the red spectrum, while the output are the black points. And as you can see, there is overlap and consistency within the error bar, stating that we're doing a good job in reproducing what we expect to have. So let's go to the real stacks then. We have done all what we could do in terms of forward modeling. We know how accurate we can be. We know how to properly ingest the uncertainty in our error budget. And so we can go to the real data and apply the same technique. And that's what we obtain in terms of surface brightness profiles as a function of the different halo mass bin for the optical selected groups in the local universe, and similarly for the spectrum. And as you can see, for the spectra, it's a bit more tricky in the sense that you cannot get the real, the same high signal to noise we could get in the stacks, in the mock stacks, just because the statistics is different there. But we could retrieve actually with accuracy the temperature of the group. And so the very first experiment is to retrieve the X-ray halo mass relation and actually to expand it down to the lowest possible halo mass spins, so down to Milky Way type groups. The black points here are what we obtain from the stacks within R500 and extended up to the very region R200 for the very first time for Milky Way type groups. And as you can see, we have relatively very good agreement at the very high masses with the EROS-1 data by Bulbul 2024. We are consistent with what obtained through individual detection, but we could push it down to Milky Way groups. Actually confirming that the observed scaling relation for groups for clusters, are valid also at the group mass scale. So we just extend the Pratt et al., Visari, Q et al. 2022 relation are all within the error bars. Relatively good fit. When comparing then with the prediction of different hydrodynamical simulation, what you could see here is that again, the black points here are the data obtained from the stacks, while the gray points are the one of magneticum, and the other shaded region are from different hydrodynamical simulation. And I would like to point your attention here in the region of the groups here. As you see, Eagle and luminosity and G are deviating quite substantially, not only from our results, but from any other results in the literature. And this is not a new result. This was there since a few years ago, while Flamingo is doing a relatively good job, well, in this region here, but once you move to the poor cluster and massive group regime, also from the X-ray luminosity mass relation, you can see that we start to have a little discrepancy. Similarly, we tested and we explored down to very low X-ray temperature, the mass temperature relation by stacking obtained through different techniques. So either by subtracting the background or by fitting together background and X-ray signal from the groups. And so confirming again the best fitting relation of the past and providing also calibration down to 0.5 kV for the very first time. But all this informed us to do something else, which is the real result we are after, which is how much hot gas mass we have in groups and whether this is redistributed and pushed out of the virial region through the AGN feedback in such small virialized systems. And so to do that, again, it's a quite tricky business. Getting the gas mass from average properties like the surface brightness profiles and the average temperature of group is not easy, in the sense that there are many different sources of uncertainty and many different aspects that needs to be calibrated and tested. And so to inform, again, our procedure, our processing of the data to infer the gas mass, we actually tested all the possible sources of uncertainty in a forward modeling approach, again, through magneticum. And so since the gas mass is retrieved from the surface brightness profile to get the electron density profile, assuming a metallicity, assuming a temperature, what we did is that to test all this assumption, so we test the assumption of setting the metallicity of the groups to 0.3 solar, which is the only assumption that is applied throughout the literature everywhere. But we know that there is a large scatter around the average temperature of groups. We could go from 0.1 solar to 1. And so we tested all possible effects of metallicity and temperature assumption from the halo mass proxy to test what effect could they have on the X-ray emissivity of the gas in order to inform our error mass budget. And so this is just a test here of how the temperature assumed might be consistent with the real temperature in magneticum, and what is the effect on the X-ray emissivity by different assumptions on the gas. All this was included in our error budget to get finally to this, which is the gas mass fraction, hot gas mass fraction as a function of the halo mass normalized to the cosmic value. Okay, so 1 is the cosmic value, which means that any system getting there is closed. The fraction of gas in the hot gas is the same as the baryon fraction, the universe at the same redshift. If you are well below, it means that not all the baryons are contained in the realized region, but they must have been somewhere else. More likely, according to what we know from the dynamical simulations, they must have been pushed far away from the virial region and towards the further out towards the filaments or outside of the node. And so what we have here is that the blue points are obtained from the stacks through all the assumption we have done before about normalization, about the average temperature of the groups. And the error bars, as you see, in particular in this region, both due to the statistics and the assumptions we have made, are quite large. But this is the only way through our model to have a robust estimate of the gas mass. And we included also here the purple square, the result based again on eROSITA, but on a different sample. We are sampling mostly groups in IFE due to the small area. We included also the result of Liskova et al. 2023 based on the stacking of the checksmate clusters in the Russian sky. Okay, so we could explore them in a consistent way through the same data from Milky Way-sized groups out to massive clusters. And as you can see here, within M500, groups contain a bit less than 10 to 20% of the cosmic value, while if you move up to M200, cluster becomes complete closed system. They contain all the baryon they are expected to contain. Nothing else is pushed out, if not redistributed within the cluster itself, as already shown at the beginning of the talk and predicted by other dynamical models. For groups, the situation is very different. Most of the gas is pushed out of the virial region. But is this consistent? Well, this is just for a consistency check. Sorry, with eROSITA data. That even if we go in a very, very tiny area in the very local universe, which is the only region where eROSITA have enough signal to noise to say something about the gas mass fraction, we are consistent with the results of the EROS-1 data. But what happens if we go to compare with other dynamical simulations? Well, the situation is quite different. Here is that this the different hydrodynamical simulations are grouped depending on their implementation of the feedback and their calibration. All hydrodynamical simulations are calibrated against observable in the local universe. Most of them against the galaxy stellar mass function, but many also against the gas fraction of groups. And so a few of them, like Bahamas and Flamingo, have been calibrated compared to the X-ray selected gas mass fraction. And so they tend to overestimate just because they were calibrated towards higher value of the gas fraction, around 10 to 13.5 and 10 to 14, while TNG and Millennium TNG, Illustris and Millennium TNG are far off. They've been calibrated only against galaxy observable, halo mass and stellar mass fraction, probably star formation rates and the Magorian relation. But as you see, they overpredict too much the fraction of baryons in groups in terms of hot halo. This is because respect to Illustris, which was the very first implementation and has this very weird prediction of the gas mass fraction, while in Illustris the feedback was extremely strong, depleting the gas completely of gas. It was modified in Illustris TNG, but to an extent that is no longer representing the hot gas fraction in groups. Magneticum is doing the best job, actually, but Magneticum was calibrated against X-ray scaling relations and clusters. And it's implementing the feedback in a way to maintain those scaling relations, which we observe were consistently expanded out to very low masses. So they're consistent also in the simulation. And just here, I would like to highlight that this has been brought to several conferences now as something new. It was not new. The discrepancy between Flamingo or Bahama XXL respect to our data is not new. It's not new because we already observe here an overestimation by the green shaded region compared to what was already known with cluster and poor cluster. So it's not that our observation are particularly lower than what was observed previously, but there was already a kind of discrepancy with past results. So that's something I found quite interesting, that when we ask ourselves whether the simulations that can actually produce best the gas properties that we observe are able simultaneously to reproduce also the galaxy properties of the galaxy population of the visualized halos that we are considering in our analysis. And this is what we found. It's a quite complicated plot, but it's only showing the position of the main sequence of star-forming galaxies in the local universe in the different simulations. So we start from Magneticum, Simba, down to TNG. Why? Because Magneticum is the one agreeing the best in terms of gas property. Simba, it's something in between, is this gray line here. TNG is the one with the largest discrepancy. And so what we did is just to observe how galaxies are distributed in the star formation rate stellar mass plane, and they are placed in this histogram just as a function of their distance from the main sequence of star-forming galaxies, from the peak. If they are here, they are starbursts. If they're down here at 0, they are sitting on the main sequence, and here they are just completely quiescent. So different histograms are referring to different stellar mass spin, very massive in purple, intermediate mass gray, and then the about 10 to 10 solar masses, the blue histograms. The solid histograms are representing the observed distribution in manga, which is the IFU survey, the SDSS, while the dashed histogram is the one obtained from the hydrodynamical simulation. So if we go in this direction, you can see there is a better and better agreement with the data. Better agreement, what it means. Okay, Magneticum is overproducing, is overquenching everything. Is overproducing a large fraction of quiescent galaxies, every tiny fraction start forming ones. If we proceed in this direction, we see that Illustris is doing much better. Okay, is reproducing, if not the very same distribution, this is artificial in the sense that all those galaxies should have 0 star formation rate, something which is not observable in the universe. We have no galaxy with 0 star formation rates. It's at the maximum 10 to the minus 3. So those are artificially pushed here with a Gaussian distribution, but they should be far away to -infinity, okay? But anyway, going in this direction, you see that Illustris is doing the worst in terms of gas fraction, but is doing the best in terms of galaxy population. And in this direction, instead, we have the other situation. So there is no, the message here is that there is no hydrodynamical simulation at the moment able to reproduce simultaneously both the gas fraction, the X-ray properties in general of the bulk of the realized halos in our universe, and at the same time reproduce also the properties of the bulk of the galaxy population in the local universe. And the same is observed, for example, in this famous plot, which is mostly used to highlight the efficiency of star formation of galaxies, of Milky Way type galaxies in groups about 10 to 12 solar masses. And I would like to show this plot to highlight both that this has been obtained from Victoria in my group through the stacks as a function of the stellar mass, and it's the very first calibration we have, up to 10 to 12 solar masses of this relation, which is not inferred from scaling relation like through semi-empirical models, but it's the real first observation and calibration of the of such relation, which is showing the ratio between the stellar mass of the central galaxy and the halo mass as a function of the halo mass. Usually this is shown to show the very high efficiency in forming star or amassing stellar mass of the Milky Way-type galaxies and the very low efficiency of group and cluster galaxies. But once we go to compare the relation with the prediction of hydrodynamical simulation, as you can see, again, magneticum is not doing that well, although, as a caveat, it's very difficult in simulation to disentangle the stellar mass as we would observe through observation and the whole stellar particle associated to a galaxy. We could include the intracluster light, the intergroup light. So it's a bit higher because we have difficulties in defining the stellar mass as we would do in the observations. But anyway, there is a large inconsistency. And the same is true for Illustris and all other simulation we tried. So it's very difficult to have a simultaneous consistency in the prediction of the gas properties and the stellar mass property. And I would like to touch the last point, which I think is a kind of summary of what we observed. We use the magneticum not only for our forward modeling, but also to check what might happen that make groups so depleted of gas compared to those that are quite X-ray bright in the local universe. And so to check that, Ilaria went to look at the history in terms of AGN activity, of feedback in those groups by picking up the very bright one, the orange lines I will show here, and also in the other plots we'll pick the very bright groups in magneticum, 1 sigma above the X-ray halo mass relation, while the blue curve pick the very faint one, 1 sigma below. Okay, so as we see in terms of energy injected into the medium as a function of time, we do not see much of a difference between the two type of galaxy groups, if not in the very local, in the very recent time, okay? Below redshift 1, let's say. Something happened below redshift 1 between that might differ between the bright and the faint one. What we see is that in terms of halo mass, actually those that tend to be bright, so the blue curve here in the gas fraction versus halo mass relation tend to be those with the smallest black hole masses, while the most depleted one tend to be those with the highest black hole masses, a fixed halo mass. And that's something already telling us something. But what Ilaria could reconstruct is that it's not only the injection of energy through the feedback to the of the supermassive black hole that might play a role. What we do see is that, at least in magneticum, also the place, the location in the cosmic web where this group are sitting might have a role, might play a role as well. So if you focus on this plot here, we see it's a function of redshift, so from redshift 1 to redshift 0. For the X-ray faint and the X-ray bright, we have cumulative distribution as a function of overdensity, dark matter overdensity. So if you go in this direction, we are sitting in a very dense part of the universe, in this direction in a very low density region. And as you can see, at all redshift, the X-ray bright tend to be sitting in very high dense dark matter regions, which means the nodes of the cosmic web. While if we go to look for the X-ray faint, we tend to find them mostly in filaments, or not even in voids, but also in filaments. And so the history of mass assembly that Ilaria could reconstruct to magneticum is that there is a striking difference between the X-ray bright group and the X-ray faint. They start with slightly different masses. X-ray bright start with lower masses, but they accrete a lot along the history just because they are sitting in the nodes And in a notch, you have a lot, you are more likely to accrete from merger through other groups. Faint groups instead are born with slightly lower masses. They stay in very quiet low density region. They just accrete from the surrounding medium through accretion and not mergers. And they increase slightly the mass, but most of the mass is lost a very high redshift to the stronger activity of the AGN, when the AGN is also highly accreting and pushing a lot the gas outside of the virial halos. So X-ray bright group are depleted in the past, but then they accrete a lot along their history, and they have gas replenishment through the mergers. While the X-ray faint are gas depleted at very high redshift, but sitting in a low density region, they do not get the same chances of accretion. They just accrete not a lot of gas, but mostly dark matter from the filaments, and they stay gas depleted. And this is why below, once we go to redshift 0, we see they as faint, while the X-ray bright are replenished of gas, and they are again very bright in the X-ray. And if we go to compare this picture with observation, in effects, we kind of see something similar. We see that the X-ray, if we go to look in the across the scatter in the X-ray luminosity halo mass relation, we see that the faint, which are sitting here, are below the relation, and they are highly concentrated. The high concentration in groups, in halos, in general, means older age, older formation time, while the brightest one tend to be flatter, and so indicating higher merger activity. And if we look for the location of X-ray bright and X-ray faint groups in effects, we do see that the red, so the X-ray bright, tend to be more likely nodes, while the blue, the X-ray faint, tend to be more likely in filaments, like magneticum would predict. But obviously, this is just magneticum view. Okay, we tested only the prediction of one simulation. There might be other views, and indeed, if we test the prediction of the energy injection of feedback at different times through different simulations, here we have lucidity and G, Simba, magneticum, and astrid, the timing of the time injection is very different. It's not only where the feedback is acting, it's also when it's acting in the past. According to magneticum, is already starting and Simba's way a very high redshift, while for lucidity and G and astrid, it takes much more time. For Simba, everything is completely and push away from the virial region already by redshift 1.6, while for lucidity it's taking much more time to get to the results. Okay, so it's not only where this is happening, it's only when, the different timing of the process. And to investigate then, we design Empower. Empower is an ESO public survey, CAMOS public survey, 150 nights to observe roughly 900 galaxies above 10 to 10 solar masses in 3 different epochs. It stands for Emission Line Mapping of Galaxy Population Cosmic Web Environment. At the beginning, it had a very different name. If you want to know the story, ask me later. But anyway, so it's 150 nights, and we will observe 300 galaxies in 3 tiny redshift windows to pick 3 different epochs, key epochs in the cosmic star formation rate history of the universe. So when at the rise of the cosmic star formation rate density, at its top, and then when the quenching of galaxies should be starting or should be very active, in order to depict whether the environment has any role in that environment, in the sense that interplay between the gas properties and the galaxy properties, because they are heavily intertwined, in particular considering the circumgalactic medium, the relation between AGN feedback and the thermodynamical properties of the circumgalactic medium around galaxies. And so we want to explore whether the flattening of the main sequences related as proposed in the literature to the halo mass passing from hot to cold accretion at different halo masses. And so to do that, we will observe not only galaxies in different locations in the cosmic web, in cosmic and general diffuse south, but also in particular region, in massive clusters, in massive groups, by considering also 2 massive clusters at each of the 3 epochs, and the distribution of the galaxies in terms of halo mass and filaments or nodes location. And this, and this should this will complement the already available data in terms of X-ray, for example. The general diffuse south cosmos fields are wealthy in terms of ancillary data, in terms of XMM and Chandra observation, and this will let us relate what we observe with CMOS with available information on the gas mass in the X-ray groups, and by stacking also in the average population of galaxy groups and clusters. And so we will link the result maps provided by Empower for these 900 galaxies with their environment, with their availability of gas, to build not only, to reconstruct not only where the different feedback and quenching processes are active, but also where in time this is happening, to give the strongest constraint to our hydrodynamical models. So I list there my conclusions. The very main point I wanted to make is that we need to go through different means for selecting galaxy groups if we really want to study the X-ray properties. So we cannot select them in the very same properties we are studying them. The X-ray selection might provide a bias. The optical selection is not perfect, but it might provide a general view of the average properties of groups. They are actually depleted of gas, so the effect of the AGN feedback in terms of pushing away the gas is clearly visible in our data, but we need to go back in time to understand not only how much it is efficient at different halo masses, but also when the process is happening to constrain our hydrodynamical simulations. And I would stop here.
Thank you. Very clear, insightful talk. So now question.
It's very, very nice. So at the beginning of the talk, you show something about simulations via the magnetic. So you simulate the X-ray emission of eROSITA via the magnetic, and basically you derive all the X-ray and gas clarify. So when you compare all your simulations, so the TNG, Lastris, so do you do the same? So do you do the post-processing? And when you compare with the data, so are we seeing apple to apple, or we see raw data with raw data?
Okay, when comparing our data with all simulation, we treated all the simulation in the same way, to be fair. So it is with a prediction. There is no passing through 16 Fox to get what we would observe with eROSITA. We can do that with magneticum. We are currently doing that with Flamingo, and the aim is to produce the same data for all simulation to compare apple with apple. Also, one simulation against the other, but not for the plot I show. No, we didn't have that. It's a work in progress.
Christian?
From an observational point of view, what do we currently know about the molecular gas content of these systems?
Nothing. Nothing, very easy. We know something about galaxy clusters, but that's the only halo mass regime where we have available data. For the groups, there is absolutely nothing.
Can you go back to the complicated plot with
there are many.
the one that you mentioned was the one with the galaxy?
When I say what complicated, yes.
Yeah, the one with the galaxy properties. Yes, this one. I struggle to understand what is the in the X-ray in the X-axis. What is that? It's the difference between.
Is the distance from the main sequence. So you take the main sequence position as a reference, you just estimate how far away is a galaxy from it. So if you move in this direction, it's a positive difference. So it's just above the main sequence, and below here, a 0 is the main sequence, while below down here, you have the quiescence region.
Okay.
So it's done just to combine everything in the same plot at different halo mass. At different stellar masses.
But the total stellar mass inside these objects, is it recovered or not?
We are
because you mentioned then that in for magneticum, if I understood.
Yeah, the difference might be in both directions, star formation rate and stellar mass. If you end up with it, this is a comparison between galaxy populations, which means that magneticum is not able to reproduce the same distribution in the star formation rate, stellar mass plan in general. So it's either producing too much massive galaxies that are overquenched, or low mass galaxies which are overquenched, much more than what is observed. Through MANGA, the SDSS, we know that still we have the majority of star-forming galaxies at 10 to 10 solar masses, for example. And most, if you go at 10 to 11, most should be quenched. For magneticum, everything is quenched. So the majority are anyway down here rather than here.
First of all, thanks for the very nice talk. So my question is about the halos with mass in between 10 to the 12 and 10 to the 13. I mean, I think it's reasonable to expect that in this regime you have both groups and individual galaxies, maybe. And so it's a regime in which the stellar mass is a non-negligible fraction, maybe of the baryon fraction. So I would like to understand better if you are selecting only the groups, if you are including individual galaxies, massive galaxies that can have halos in this regime, and if you account also for the contribution of the stellar mass baryon.
Okay. So we have tried both, and it depends on the output of the detection algorithm in the optical. In the sense that the Young et al. Catalog, for example, the Young et al. Or Young 2021 right now is the newest version of the algorithm, tend to select all galaxies, including the isolated ones, providing a halo mass proxy, which is based on the stellar mass of the central galaxy through scaling relation that just we want to calibrate. In that particular case, we've tried with and without those galaxies, just for checking whether having or not a detected satellite might play a role, but we didn't find any substantial difference. The Roboton catalog, the one used for gamma, and which is going to be used also for waves, do not include the isolated galaxies, but pick only the groups with at least one satellite, so two galaxies in the group. And even in that case, we've done the same exercise. For isolated galaxies, we use the central mass of the galaxy for having a proxy of the halo mass, and we didn't see, by including or excluding them from the stacks, we didn't observe a strong difference. In terms of baryon, I on purpose refer to the hot gas fraction because we do not consider yet the baryon fraction. I didn't include the stellar mass for a reason. In the gas fraction halo mass relation, the halo mass is based on the stellar content of the halo. So it would be a circular argument if I enter then the same quantity in the baryon fraction. We will revisit them, the relation, but by using the weak lensing masses for the X-ray axis, so that we then can include also the stellar contribution in the baryonic fraction.
There is a question online, so how we can proceed? Okay. Please.
Hi, can you hear
Can you
me?
speak loud? Loud?
Yeah, can you hear me?
No. Try to shout.
Can you hear me now?
It's very flavorful.
It's not possible to hear me.
Increase the voice. Try to speak anyway or write in the
Can you
chat.
hear me now? Sorry. Is it better?
Try.
Yeah, try. I can hear you.
Can you hear me?
Yes.
Oh yeah. Now yes.
Okay. All right. Okay. Sorry, there was technical problems. Thank you for a presentation, and I really enjoyed your illustrations very clearly. I'm not an expert in this field, but I was a bit confused in the beginning how you were explaining the reason for the optical selection of the groups was, for example, the effect of AGN feedback. So I didn't understand what happened with AGN feedback in the groups which were selected by X-ray selection method and why it was different. And in general, when I think of AGN, they are rare objects. So was it some sort of burst of AGN activities that provided a lot of AGN feedback? Or in those groups where the AGN feedback has done its job, was it some sort of here and there AGN feedback activity by one or how many galaxies that provided that? Can you explain a bit more?
Yeah, sure. Okay, so what the models, what the hydrodynamical simulation tend to suggest, because there is no way for us to observe directly the effect of the feedback. We can. There are many clusters, many more than groups, where we do observe strong jets, and according to energetics that we can estimate from the AGN accretion and the kind of energy they inject in the observed cluster where we do actually observe the jets. We know that the quantity of energy they can input into the surrounding medium is enough. It's more than sufficient. Just a little fraction of it would be more than sufficient to completely push away the gas from the halos. So according to simulation, the fraction of this energy of the feedback generated by the AGN is able to affect the core in massive cluster by redistributing the baryons, the hot gas within the core of the cluster, mostly affecting the CGM of the central region of the central galaxy. While for groups which have a much lower binding energy, a lower potential well, the same fraction, the same fraction of the AGN energy can completely deplete the group of its gas. Okay, it would be sufficient to push away the groups outside of the rear region. Okay, and that's mostly the AGN according to simulation of the central galaxy. The AGN of the satellites might play a role as well locally by affecting mostly the CGM of the satellites, if it exists, which is still a big question in groups and clusters. But it's mostly the supermassive black hole of the big bright group galaxies that do most of the job. This is happening according to what we see, a very high redshift, much more than in the local universe, just because the active phase of the AGN is at the peak at cosmic noon around redshift 2, when the accretion is the highest, when the merging rate is the highest, and so also the feedback is the highest. And it might affect not only the surrounding media of the central galaxy, but extend to affect through strong jets also the rear region of the group. And that was the other question. If it's recurrent or a constant or episodic. That's many of us are after that for constraining the duty cycle of AGN. I don't think we have few indication about how this duty cycle might be. I mean, quite episodic, or in the local universe, we have some indication that there is a recurrent maintenance radio activity of the central AGN, but we don't have, I think, consensus about the duty cycle currently, if not from the suggestion of the hydrodynamical simulations. If anybody else disagree, please say something.
If I can ask a last question about empowers. Do you have prediction about empowers, in particular to validate a model that you suggest about X-ray bright and X-ray faint groups? Because you should know already the field, and so you have kind of key features that you want to investigate to probe how efficient are X-ray bright or how no efficient are X-ray.
Yeah, that will require not only empower. Empower is one piece of the puzzle. We need first to go back to the old data, very old data, the Chandra and XMM, to stack for the optically selected groups. Now the catalog are available for Cosmos and soon for Chandra diffuse south. So we're going to stack there and relate then that result to the galaxy population. Still, I think we do not have any constraint, not even at intermediate redshift, about how the relation I show are going to evolve, not for clusters. We know it only, we have indication only for massive cluster, but not for groups. Once we know what is going to happen in terms of X-ray properties at intermediate and let's say 1.5, so at the peak of the cosmic star formation rate density, we might relate that with what we will observe through empower. So no, there's no clear prediction because we don't know how we have different evolution of such scaling relations through different simulations, but still no observational constraints.
Okay, thanks, Paola.